Okay. So previous class, previous class we discussed about maps, right? What is a map? Basically, map F is just like a machine. Okay. This is a map F. What it will do, it will take the variable xn and it will give you the next future variable, that is xn plus 1. Yes. So again, this xn plus 1 will be fed again to this map and again it will give you that thing, xn plus 2. Like that, you will generate the sequence xn plus 1, xn plus 2, so on, so on. It will go. What is our aim? Our aim is to understand the behavior. Our aim to understand the behavior, of the iterates over a large number of iterations. Fine, good idea. Okay. So, and after we understood this one, we took an example. That is, let us say xn plus 1 is suppose 5xn, and say xn plus 1 is equal to say 0.1 xn. These two examples we took, and what we came to know, that if you start from any initial conditions, x0, you start. What is the behavior? What is where xn goes to as you take long number of iterations? That means n tends to infinity. So as n tends to infinity, what happens to xn we saw last time? Yeah. I mean, if you take initial condition 0.1, so what will happen? It will be 0.5, then 0.25, 0.125, like that. It will go to 0. So for any IC, I think I made it wrong. For any initial condition less than 1, it will go to 0. Okay. But any other initial condition, where it is greater than 1, okay, or even equal to 1, even if you make it equal to 1, okay, it will still go to infinity as n tends to infinity, right? So you can see here it always goes to 0, and another case is it goes to infinity, that is diverging. Okay. So okay, let us see for this example what happens. Any initial condition you take, even initial condition like mod x0 less than 1, okay, if you take mod x0 less than 1, what happens? What is x1? 0.1. What is x2? x3. So any you take, it will go to 0 as n tends to infinity. But if you take mod x0, say equal to 1, what happens? The same thing will happen. It will still go to 0 as n tends to infinity. But if you make it greater than 1, that is x0 say 2, then what will happen? x1 is equal to 0.2, x2 equals to 0.02. So it will decrease, right? So what happens? It tends to 0 also as n tends to infinity. Isn't it? Agree? So in this map, only one case is possible. That is, whatever you do, wherever you start, it will always go to 0 as n tends to infinity, right? But you see, these are two different types of maps. I mean, these are all linear maps. It's a linear map. In a linear map, you can see it has only two possible cases. Linear maps are not that interesting. Why? It only shows two possible cases. One case is it can go to infinity, or it can go to some particular value. Okay. I mean, it can converge to some particular value. Only these two phenomena it can exist. Now, some of the scientists, they thought that why we need to consider linear maps. Okay, why we can consider non-linear maps also. Okay. Yes, definitely you can do. So therefore, you can still consider maps like xn plus 1 is equal to say 5xn square, something like that. Okay, and still study the dynamics. So maybe this I will leave it to your homework, like try it. Okay, what happens if you do xn plus 1 is 5xn square and then 0.1xn square? What happens? Then people thought that why we need to make it non-linear, like only non-linear terms. We can have a mix of linear and non-linear terms. So if you want to have a mix of linear and non-linear terms, then came the scientist like Robert May, okay, from MIT, who is a population scientist. He derived that in population, suppose tiger population, okay, tiger, maybe deer population, say deer population. So what happens to deer? Deer populate and population increases, and deer gets eaten by lion or tiger, their population decreases. So population keeps on oscillating, it can decrease and it can increase, but this needs to happen so that the population remains under control. Okay, it can never be a constant, but it can remain under control. Yes, it you therefore this is one of the reason why you never see the number of deers keep on increasing and take over the human population. Okay, I mean, there are some things which people don't consume. There are some animals which people don't consume. Any examples? I mean, any examples? Okay, grasshopper. Okay. So grasshopper people don't usually consume. Yes. Suppose let us assume they don't consume. Okay. But then if no one consumes, then why the population doesn't go increasing and they take over our human population and they have their own house? Yes, possible, right? I mean, we would have seen they would have a house here, they would have a house there. They would take the number of students in this class, it would fit. The same number of grasshoppers, it would fit. Yes. So why doesn't happen? That means it decreases and increases in such a way that the balance is maintained. So you cannot design a population model as it is. You have to design keeping these two in mind, that its population can increase and also in some cases the population can decrease also. So therefore Robert May planned this new model xn plus 1 is r into xn into 1 minus xn. Okay. So this is the reason why you have a r. R is known as the reproduction factor. R is a reproduction factor. Okay, it's a biologist, I mean, interpretation I can give. So you multiply it with your previous state, fine. See, the future state depends on the past state, right? I mean, if you don't have the past state, how they will reproduce? Okay, so you need the past state to reproduce. So then the new state is there, but keep in mind that there is 1 minus xn. This responsible for decrease in population. Decrease in population. This is responsible for increase in population. So therefore, it is a good model. So it accounts for both increase and decrease in the population of some individual or species X. Okay, fine. Now, when you took this model, were you able to predict what kind of behavior it can give? That's the first question. Since it's a 1D map, since it's a one-dimensional map, the question is what kind of dynamics it can give. We know that it can converge to a point as given by your previous 1, 2, 3 examples, or it can go to infinity also. But turns out it displays two more interesting things other than that when you make it non-linear. That is, it can show periodic orbits, it can show chaotic dynamics. Okay, that we saw in our previous class. I suppose you remember it. We saw in our Python coding, right? We took two nearby initial conditions, 0.001, 0.00001. Very tiny change in initial condition. And we plotted the blue and red together. And we saw that over the number of iterations, they both changed. You remember? Do you remember? How many of you remember that? Do you remember? You remember, yes. So therefore, that is known as sensitivity to initial condition. So therefore, I named the video as logistic map and SDIC. What is SDIC? Sensitive dependence to initial conditions. Okay. So this is the idea. Okay. Now this map, I will tell you. So when you took R1, say 2, when you took, sorry, uh, when you take r equal to 2, you saw a fixed point, isn't it? You saw a fixed point. When you took r equal to say 3, you saw a period 2 point. A period 2 point. Okay, period 2 point. What is a period 2 point? I hope you remember this guy. You can see, let us consider let us write it here so that people can understand. When r equal to say 2.6, what you see? A fixed point, isn't it? Can you see that now? Yes. Why? Because at r equal to 2.6, you just have a point. Xn, x value of xn is just a point. This is xn. It is just a point. So it's a fixed point. That means as you iterate your map, it goes to a particular point. Okay. Now see very carefully at x equal to 3, something really interesting happens. What interesting happens? Like at x equal to 3 here, you can see that this guy doubles into 2. That means it oscillates in between this point and this point. So when you plot the data set, of over a number of iteration, you will see something like, say, let me not guess, maybe 0.5. This is something 0.7. So it will be like 0.5, 0.7, 0.5, 0.7, 0.5, 0.7. The data set will be like this. Why? Because it will be iterating in between the two. Agree? So when suppose this is n equal to 10 number of iteration, n equal to 12, n 11, n equal to 12, 13, 14, 15, right? Agree? I just showed some part of it. I mean, I took a chunk of it and I analyzed the data set. Okay. So I saw for n equal to 10, it is showing 0.5 value. This is xn. So when this repeats again, when the 0.5 you see it again at n equal to 12, at n equal to 12, you see 0.5 again, right? So xn is equal to xn plus 2. If it's a period 2 orbit, xn will be repeated after 2 number of times. So it is xn equal to xn plus 2. Yes, it is valid for n equal to 11 also. X11 equal to x11 plus 2, x13. Is it true? Is x11 equal to x13? Yes, it is. Take n equal to 10 and apply it here. X10 equal to x12. So x10 is equal to 0.5. What is x12? 0.5. Right. So if it is a period 3 orbit, what will happen to the data set? For a period 3 orbit, xn plus 3 is equal to xn, isn't it? For a period 4 orbit, xn plus 4 is equal to, who is eating my cursor? Okay. Xn plus 4 is equal to xn. So for a general period k orbit, for any periodic orbit, k orbit, what you will have, xn plus k is equal to xn. Okay. That's how it is. Okay. So this is a condition. I mean, we'll learn more about periodic orbits later. But yeah. So when r is equal to 3, what we saw? Can you tell? Hmm? For r equal to 3, everyone should say a period 2 orbit. But still, I will tell that it is not correct. I mean, something we are missing here, some details we are missing. There is some detail we are missing here. But that is too much deep. I will tell you when time comes, right? Okay. When r equal to 3, a period 2 point, when r equal to say 3.54 something, 3.544, what you see? What is 3.5 something? 3.5 is here, 3.54 is somewhere here. So at here, what you see? At this guy, what you see it? Period 4 orbit. Okay. So same thing. So let us see. If you go a bit more, yeah, maybe 3.3 point, maybe bit more, 3.545 maybe, you will see a period 8 orbit. When you go just here, when you go just here, this part, this part. So it's a period 8, 1, 2, 3, 4, 5, 6, 7, 8. Period 8 orbit. You will see a period 8 orbit. Yes. So, but when you go back, like r equal to say 3.6, yes, 3.6, what you see? A band of noise. When r equal to 3.6, you see a band of noise. That means it comes back to this guy. It's totally a band of noise. It's a strap. It's a strap of dark black points. It's a stream of black points. Okay, that means it's a chaotic orbit. Okay, so it's never repeating. Why you saw only 2 points? Because it's a periodic orbit. Only it oscillates in between 2 points, right? It never goes to some other point. So it has nothing to do with other points. It only does 2 points. But in a range of black points that was plotted, you saw only a stream of black points. What does it mean? It never repeats. If it never repeats, then only it will generate a stream of black points, right? Otherwise, there is no way. Why? Because if suppose this one, let us see how these black points are generated. You iterated, next iterate is here, next iterate here, here, here. You are still plotting the iterates again and again. Never it's coming to repeat. I mean, after this iterate never falls back. So it keeps on continuing to make the stream. So therefore you see a stream of black points at every parameter step. Okay. So that's the idea, and that's why you see this, I mean, chaos. Okay. So at r equal to 0.6, you see chaos. Okay. So can you see something important is happening and something very nice pattern exists here? Of course, chaos, we already know it. Chaos is something, when you call a data set to be chaotic, when it exhibits sensitive dependence to initial conditions. Tiny change in initial condition you put in the model, it will give you different time series. Okay. That we saw in our last Python code. Okay. So now we know chaos is there in this system. Fine. But can you see a pattern in this writing? Can you identify a pattern here? What pattern is? Hmm? Yes. Yes. Not 2 raised to 2, like doubles. Means every time you multiply by 2. I mean, you see a fixed point. So fixed point is a period 1 orbit. It's a fixed point. After that, you saw it is doubled, like a period 2. 1 into 2, 2. After that, 2 times 2, it went to 4. After that, it went to 8. Okay. After that, you can still see 16. Okay. After that, it went to chaos. Okay. I mean, it is doubling, 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 and going to chaos. Right. So, therefore, this is a mechanism of obtaining a chaotic signal. Okay. It's a mechanism of obtaining a chaotic signal, and it is true for any discrete map of any dimension you take. It is such a standard route that people have obtained. And this standard route, you remind yourself, it would have not been possible without a computer. This thing you saw, I gave you assignment. Everyone plotted their xn versus r plot, and you came to know how different it was from your imagination. Okay. So no one could decode that chaos was existing in this system at the first place without a computer related plot. And second, you cannot discover this novel mechanism of how to obtain a chaotic signal. Okay. So you obtain a chaotic signal via this. So this occurs, this is known as a period doubling route to chaos. It's known as a period doubling route to chaos. So period always doubles. 1 goes to 2, 2 goes to 4, 4 goes to 8 to 16, so on till chaos is achieved. So this is one of the mechanisms to go to or generate a chaotic signal. One of the mechanisms. There are so many other mechanisms, okay, which you will learn more if you go more detail into it later and all. But we'll not go too much detail into that. That comes with experience. So we'll just discuss this one here. A period doubling route to chaos. Okay, fine. Okay, okay. Now let us see something interesting. So I don't know if so actually this is a fractal. I mean, we'll come back to this when I will be teaching you fractal. But this picture you are seeing right now, what is this diagram known as? Anyone? Hmm? No, the map is logistic map. The map is a logistic map. But what is this figure known as? What is the figure one? Hmm? Yeah, but you are telling only some parts, some chunks. See, I suggest you should watch the videos when I upload. So, what is happening here? I mean, everything is basic common sense. Nothing is outside of the box or you have to remember or something. See, you are analyzing how the map behaves as the parameter R changes, right? So R is a parameter. It's like an AC remote. You can change or decrease the temperature, increase the temperature, decrease the temperature. So we tell it as variation of the parameter. We never usually tell, I mean, decrease or increase the parameter. We vary the parameter. We vary the parameter and observe how variable x changes. So this is a parameter and this is a variable. We don't have control over variables. Do we decide the map and we put one initial condition and the map and the parameter value and the variable takes the value. We cannot tell that the variable should go to 3. We cannot tell. But we can always change the parameter and tell that the parameter should go to 3 or 4. Agree? Yeah. So this is a parameter and that is a variable. So you are understanding how the variable changes as the parameter varies. So since one parameter you are changing, and with that one parameter you are seeing a bifurcation. There are bifurcations we will discuss in some classes. This is known as a one parameter. One parameter. How many parameters you are seeing? R only. You are not varying two parameter, only one parameter. So it's a one parameter bifurcation diagram. So it's a one parameter bifurcation diagram. Okay. This is known as a one parameter bifurcation diagram. I think in many of your capstone projects already in the papers you might have seen this diagram. Okay. So it's pretty common. And this is a fractal diagram. I mean, this behavior, what you are seeing for this simple logistic map is a fractal. Why it's a fractal? Because if you see this, what you see here, this tiny part is getting doubled to this part. Yes. Now the same behavior you will be seeing in other parts when you zoom it. Can we go back to here? Can you check here? So if you check here, what happens here? If you check here, you see something like this, isn't it? So it's a period doubling route again. So in a bigger copy, you see the small copy again. And believe me, here also you will see it. Here also you will see it. Here too. Yeah. So this is a fractal. Okay. So I mean, such a richness it has. It's very rich. Simple system, but very rich. So this fact, actually, one of the scientists he saw. Okay, he saw one of the scientists. Okay, his name is. He got astonished by this diagram. So when this figure was released in the scientific community, many persons have seen this diagram, and one of them truly admired the diagram. So he could not sleep after seeing the diagram. So he is Feigenbaum. Okay. So what happens to this researcher is like he saw the diagram and he was like astonished about this diagram. So and he had a very curious nature. So inside the university he used to study, and late nights in the university when everyone slept, he was wandering in the the outside of the university alone. Okay. So what happened to him? Like he was thinking about this. While he was wandering, he was not doing anything else. He was wondering and thinking about the problem. Okay, which now is not seen. Okay, so anyway, so what he was wondering about? He was wondering about this diagram. Means how this diagram could actually be constructed. Highly unintuitive diagram. Then he thought that something is there within this diagram which makes me feel like something is hiding inside it. Okay, something is hiding. Now, what is hiding? So, what he thought is when it doubles, when this guy doubled, there is a length, there is a separation between these two, and then there is a separation between these two as well. There is a separation between these two as well. Okay, then there is a separation between these two as well. Is there some pattern of this separation distance? Okay, now if you see another one is this one, like the distance from here to here, I mean till period doubling, and the distance from here to maybe the distance from here to here, from this point till this point, I mean the next period doubling. Is there a distance, some pattern behind this? So he did a lot of analysis. I mean, finding the points manually and doing it is very difficult. And due to that difficult part he discovered something fabulous. Okay, and he discovered that indeed there is a pattern. Okay, indeed there is a pattern. So he is Michel Feigenbaum, whom no one kind of believed. Okay, and everyone was telling a lot of things about him, that he is roaming around in nights alone, and the security guards were telling them that what you are doing at night, where were you in the morning, why were you not thinking in morning, why are you thinking now, so many things. But Michel Feigenbaum decoded this fact when he was wandering at night. Okay, he published that work in some journal like Statistical Physics as a single author when no one believed him. So around 1978. Okay, okay, and he found something which is this. Suppose I will tell you his hypothesis. Okay, now what he found is you measure this distance, let it call known as dn. Let this distance be referred to as dn. Okay, now after doubling to period 4 orbit, there is a separation, and a separation bit less value than dn. Okay, so let us call it a dn plus 1. So of course dn plus 1 is less than dn. It is seen. Okay, and it can be seen from here. Like you can see the distance between here to here is less than the distance between here and here. Okay, I mean it gets flatter. Flatter. Okay, so he found out that when you take the distance between them, that is dn plus 1 by dn, it is converging to some constant value, that is 2.5029. Sorry, yes, 2.5029. Okay, that means again if it doubled, okay, and this distance you call it as dn plus 2, then still you will get something like this, that is dn plus 2 divided by dn plus 1 is also 2.502. Okay, so this is the constant property of Feigenbaum. Okay, so yeah, so this also has connection. This appears in this dynamical system and in a very one-dimensional map, but this has been seen in statistical physics also in phase transitions. Phase transition means when ice gets melted to water, different state, a phase transition occurs. When a different phase transits to a different state, it also behaves something like this. Okay, fine. So now, what Feigenbaum thought is this pattern only applicable in logistic map? This is the logistic map you took. Now he thought whether this property is valid only for logistic map. What do you think? Actually, no. Actually, he tried all the maps. He tried different one-dimensional maps, nonlinear maps, He tried sinusoidal maps like xn plus 1 is some r sine pi xn. I mean, this is very different from logistic map and very complicated also. But still, he found the same period doubling cascade. He found the same period doubling cascade. Okay. And the same distance pattern holds. That the distance, the ratio of the distances after doubling and before doubling is converging to some value, 2.5 something. Okay. So it is known as a Feigenbaum's constant. This constant therefore is referred to as Feigenbaum's constant, often referred to as delta here. Okay. I mean, you can see that this figure is no more a joke. I mean, just came out of nowhere. It has some physical meaning, and only it could have turned out like this. People could do a lot of experiments only after using coding for this. I mean, after you code this up, you can do. I don't know. I don't know. Can I challenge you to code this? Can I challenge you to code this math? I mean, very simple math. That is, xn plus 1 is r xn into 1 minus xn. From r equal to say 2.624, you have to vary r belongs to 2.624, and you have to just plot this kind of diagram. I mean, it's just a challenge, like to understand how you get this diagram. So if you run this code, it will take you, it depends how fine diagram you want. It is computationally intensive. Okay. In between 2.6 to 4, if you want around 1000 points. So 1000 points means each iteration, if suppose takes 1 second, so 1000 second, how much is it? Or suppose it takes 0.5 seconds, so it's around 500 seconds. 500 seconds is around 8 minutes. Still 8 minutes it will take to plot. But if you have some good computer, gaming computer, it can take even 2-3 minutes. Okay. So definitely this will take some minutes. To, at least 1 minute it will take to compute. Okay. So not so easy diagram to do also. Okay. Fine. So, okay. So yeah, what he found also is like, if you take this guy, delta n, I mean, from this point to next point it doubled. And this point will be known as delta n plus 1. Then still that also has a pattern. Observe that this distance we are considering is in the y-axis, right? In the y vertical axis. And this distance you are considering is in the x horizontal axis. Okay. Now in the y-axis we saw a pattern. dn plus 1 by dn has some 2.5029. Now what about x-axis? Does it hold a pattern? Yes. So if you take this delta n plus 1 divided by delta n, it still converges to a value 4.66. Okay. I mean, delta n plus 2 divided by delta n plus 1 also you will get 4.66. Okay. So it also has a constant. Means the diagram we have not done, the map has done. In x-axis and in y-axis also it behaves in a particular way. I mean, it does a period doubling bifurcation. It is a fractal. More and more you zoom in, the same structure you will get. And also the diagram is made in such a way that the distance, the vertical distance and horizontal distance also scales in a particular manner. In a such a manner that all one-dimensional map, any one-dimensional map you take, will still follow these two constants. I mean, how mesmerizing it is. I mean, what forces them to do all these behaviors? I still I cannot understand. I mean, I always know about this, but I don't know how all of this can be connected. It feels that they are talking to themselves, like they are different groups. They are different groups. Like maybe I think you must have seen Fantastic Four movie, Fantastic Four. Who are there? Like ice, fire, oh, vocal, cockroach, crow, rock, and then huh? Invisible, invisible. So four people are there. Now these four people talk among themselves and save the world. So therefore now here also if you see fractal is there. Okay, fractal, it exhibits fractal. It exhibits chaos. Okay, it exhibits what else? It exhibits bifurcation. Okay, and it also exhibits, yes, a pattern, that is the Feigenbaum. Now all of these are interconnected. All of these are interconnected. I mean, all of these happen. All of this happen in this one parameter bifurcation diagram. All of this happen in this one parameter bifurcation diagram, and also in any map, in any 1D map, even any 2D or 3D maps also you can take. It will happen. I mean, how they talk with themselves, how. So therefore, this forced scientists to think about unified theory. I hope you might have heard about it. Unified theory of of unified theory of unified theory. Yeah, unified theory. So I mean gravitational pull F equal to ma, or something like that, and also how friction, all these things. I mean, why we have different equations for different phenomena? Why can't we have a single equation which represent all of the phenomena? Still being done, still being constructing, like a huge open problem. But this reminds me that still a unified problem can be there for nonlinear dynamics. I mean, it's a good problem. So I don't know. So, a great scientist has told that this Feigenbaum constant is a new physical constant fundamental to 1D maps, as pi is to circles. As when you see circles, pi is everywhere, Feigenbaum constant will be everywhere in nonlinear dynamics. I mean, yeah, it is just a surprising constant. So sometimes it needs that people see the same thing in a very different way. Okay. So the one guy who plotted this diagram did not think much about this, but one guy got totally astonished about this diagram and wandered throughout the night outside the university and found this diagram, like found this pattern. So what matters is not intelligence. What matters is how you put hard work to it and how you think the same thing in a very different way, how you look into things. So that's the way. Okay. So yeah. Fine. So shall we take a break, or after 30 minutes we'll take a break?